Welcome, my wonderful general chemistry students, to today's Chapter 6, Part 2 lecture on the electronic structure of atoms. I'm Dr. Mike Christiansen, and I endorse this message. As I consider the wonderful world of atomic structure, I'm reminded of a time. Now, I gotta confess, I was trying to think of some kind of humorous, entertaining, personal anecdote to go along with our electronic structure, but I've got nothing. So instead, I'd like to tell you a personal family story that was told to me by my oldest sister. Long ago, before I was born, when my two older brothers were just kids, my dad liked to take them target shooting with .22 caliber rifles. At the time, they were both too small to actually lift the guns on their own. You'd think that this fact, coupled with common sense, might discourage the typical father from engaging in such an activity. But my dad was anything but typical. Common sense has often been a rare commodity in my family. So to address this challenge, rather than cancel the gun shooting, my dad would take my older brothers to a shooting range up the canyon in his old-fashioned station wagon. He would then let the boys sit in the back of the car and point the rifles out the rear window. The rifles would be propped up at the bottom of the window opening so the car would hold up for my two brothers, who were too feeble to actually hold them up, being about ages 5, 6, or 7 at the time. Now, one of these excursions to which my sister was present, she watched as my dad, standing in front and just to one side of an armed rifle, angled it from outside of the car through the open rear window and into one of my brother's waiting hands. As is custom for all small boys, as soon as the rifle was in his grasp, he pulled the trigger and discharged the weapon, with the bullet barely missing my dad. My dad responded calmly by saying, "Now, David, please don't pull the trigger until I get everything set up." He then repositioned the rifle into my other brother's hands, and the same kind of thing happened again. My brothers just instinctively and instantly pulled the gun's triggers as soon as they were within their grasp. At last, when my father was repositioning one of these guns into another of the brothers' hands, the weapon discharged for the final time. The bullet zoomed past my father's head so close that it actually blew his hair up, woo, as the air went by. Now, my sister told me that she refused to ever go target shooting with him again after seeing that, and she's held true to that promise. So with that said, we'll now launch into today's lecture on Chapter 6, the electronic structure of atoms. After studying today's presentation, which will cover sections 6.5 to 6.9, you should be able to do the following. First, explain quantum numbers as detailed in section 6.5. Second, know the general shapes and names of the 4 different kinds of orbitals. Third, write the longhand or condensed electron configuration of any element on the periodic table. And fourth, know the difference between core electrons and valence electrons. As we discussed in our last lecture, an atom's electrons soar around its nucleus in a defined region of space called an orbital. You may remember that I taught you about 4 different kinds of orbitals, s, p, d, and f, and I showed you the shapes of the s, p, and d orbitals. We can think of orbitals as just being regions of space around the atom's nucleus in which electrons can go. If electrons were cars, orbitals would be their parking spaces. To be able to properly and more deeply understand how and why elements behave the way they do, we need to have a system to describe electrons with further detail. Rest assured that there is just such a system. It's called the system of quantum numbers. So each electron can be described by using 4 different numbers called quantum numbers. These numbers are kind of like an electron's address. I'll now describe each of these 4 numbers. The first quantum number is called n, the principal quantum number. This number can be any integer, 1, 2, 3, 4, etc., and describes how far an electron is away from the nucleus. For example, an electron in a 1s orbital has a principal quantum number, n, of 1. An electron in a 3s orbital has a principal quantum number, n, of 3. An electron in a 3p orbital also has a principal quantum number, n, of 3. An electron in a 4d orbital has a principal quantum number, n, of 4, and so on.
The higher the n value, the higher the electron is in energy, and the further away it is from the nucleus. The second quantum number is L, called the azimuthal quantum number. This number describes which kind of orbital, s, p, d, or f, the electron occupies. An electron in an s orbital, for example, has an L value of 0. An electron in a p orbital has an L value of 1. An electron in a d orbital has an L value of 2. And an electron in an f orbital has an L value of 3. This is shown in the following table, which I have copied from your book. The third quantum number is m sub L, called the magnetic quantum number. This number can be any integer from negative L to positive L, including 0. The magnetic quantum number, m sub L, describes the orbital's three-dimensional orientation in space. For example, you should remember from our previous slide that I just barely showed you that the L quantum number for p orbitals is 1. This means that the m sub L number for p orbitals can be negative 1, 0, or positive 1. And just what does that mean? Well, it means that these three numbers, negative 1, 0, and positive 1, represent three different p orbitals, one along the z-axis, one along the x-axis, and one along the y-axis. The fourth quantum number is m sub s, called the magnetic spin number. The spin number is the last quantum number and is equal to positive or negative 1/2. That is, for any two electrons occupying the same orbital, one of them gets assigned a plus 1/2 spin and the other gets assigned a minus 1/2 spin. If, for example, two electrons had identical quantum numbers n, L, and m sub L, then we would assign one electron a plus 1/2 spin and the other a minus 1/2 spin. This would mean that these two electrons, both shooting around inside the same orbital, are revolving around their individual axes in opposite directions from each other, like this. It's important that we have this final fourth quantum number, the m sub s number, or else we couldn't explain how two electrons can simultaneously occupy the same orbital. Why? Because the existence of something called the Pauli exclusion principle, which states that no two electrons in the same orbital can have the exact same four quantum numbers. In summary, then, there are four different quantum numbers which we can assign to different electrons and which function kind of like the electron's address. First quantum number is n, the principal quantum number. It can be 1, 2, 3, 4, and so forth. It says the distance the electron is from the nucleus. Second number is L, the azimuthal number. 0s for s orbitals, 1 for p orbitals, 2 for d orbitals, and 3 for f orbitals. Third is the m sub L quantum number. This can be any integer value from negative L to positive L, including 0, and describes the orbital's orientation. And last is m sub s, the magnetic spin number. It can be plus or minus 1/2. Now, if you want to get a look at this idea with greater detail, Table 6.2 summarizes this stuff, I think, pretty well. So let's do some problems now, beginning with question number 6 from our problem set 6. It asks us, for n equals 4, what are the possible values of L? For L equals 2, what are the possible values for m sub L? And for m sub L equal 2, what are the possible values for L? We'll go ahead and do those problems right now. You're welcome to pause the video here if you wish to try them on your own before I give you the answers. In part B, problem set 6, question 6, we are asked, for L equals 2, what possible values could we have for m sub L? You may remember from a previous slide that m sub L has values of minus L all the way to plus L and every integer in between. So if L equals 2, m sub L can equal minus 2, minus 1, 0, plus 1, and plus 2. Let's see if we can do the reverse. In question C, I'm given m sub L, the magnetic quantum number, as being equal to 2.
So what values can L have? The answer is L has to be greater than or equal to 2. The answer is explained because there's no way in which I could have a plus L for my magnetic quantum number and have an L that's smaller than that number. If, for example, L were plus 1, then M sub L would have to be equal to minus 1, 0, or plus 1. And once again, for this problem, it tells us that M sub L equals 2. So the only possible values I could have for L would be any value that is positive 2 or larger. So it could be 2 or 3. Remember that 2 corresponds to a d orbital, and 3 corresponds to f orbitals. So the answers are 2 or 3.
And now we'll move on to question 7 from problem set 6. Give the values of n, l, and m sub l for each orbital in the 2p subshell and each orbital in the 5d subshell. Once again, if you guys want to, you're welcome to try these on your own before looking at me giving you the answers.
We'll now move on to problem set 6, question 7. In part A, it asks us to come up with n, l, and n sub l values for each orbital in the 2p subshell. So I'm going to write 2p. Now remember, 2, this first number, is the n number. P tells us the orbital type. We have to remember that for a p orbital, L equals 1. Then M sub L equals negative L to L, all of the integers in between. So M sub L could equal, in this case, because L is 1, it could be negative 1, 0, and positive 1. So here's the answer. N equals 2, L equals 1, and M sub L equals negative 1, 0, or positive 1. Now let's see if we can try part B. Come up with quantum values for n, l, and m sub l for each orbital in the 5d subshell. Now remember, 5 tells me the n level, which is the energy level. D means a d orbital, and the L value for D is 2. The M sub L values then can be negative 2, negative 1, 0, positive 1, and positive 2. So these are the final answers. N equals 5, L equals 2, M sub L equals negative 2, negative 1, 0, plus 1, or plus 2.
Now we'll move on to a new but slightly related subject, that of electron configurations. And what is an electron configuration? Well, an electron configuration is a list of all the electrons in an element and the orbitals that they occupy. To determine an element's electron configuration, we have to begin by breaking up the periodic table in the following way. You'll notice that everything, all of the elements that are in columns 1 and 2, are called the S block. That also includes hydrogen and helium. although that isn't technically true in other applications. When we're talking about electron configurations, we're going to consider hydrogen and helium to be part of the s block. You'll notice that all of the elements over here in this green area of the periodic table are called the p block. You'll also notice that the transition metals right here constitute the d block. And this region of the periodic table of lanthanides and actinides are what is called the f block. So let's go ahead and do an example. We'll pretend that we've been asked to give the electron configuration of oxygen, which is element number 8. How do we give the electron configuration of oxygen? Well, what we'll do is we count from left to right on the periodic table, from the top row to the bottom row, in order, remembering that each box represents the addition of one more electron. So we start with row 1s, and box 1 in that row, which corresponds to hydrogen. And then we count left to right. 1, 2. So far then, we've counted 2 electrons on row 1, the 1s row. So we would say then that the electron configuration that we've counted up so far, just to box 2, which is the helium box, is 1s2. So once again, this number 2 comes from there being 2 boxes filled. This 1s tells us which row we are in the s block. But you'll notice that we're not to oxygen yet. That's in box 8 all the way down here. So what do? Well, we continue going, counting here, beginning with box 3, the lithium box. We count up 3, 4, until we fill up the 2s row. You guys will notice that because we filled up the 2s row with 2 electrons here, we can say that the electron configuration that we've made so far up to this box is 1s2, 2s2. But sadly, we're not to oxygen yet. We have to keep going. So we continue counting starting at box 5. Now you'll notice that this box, the boron box, is also the first box in our p block, and it's actually on row 2p. So we go ahead and count up how many boxes over we have to go until we get to oxygen. 1, 2, 3, 4. So we just filled up 4 boxes in the 2p block to get to oxygen. Hence, oxygen's full electron configuration is 1s2, that's for these 2 in the 1s row, 2s2, that's for these 2 in the 2s row, and 2p4, that's for these 4 in the 2p row, going all the way up to oxygen. Notice that if you add up the superscript numbers in 1s2, 2s2, 2p4, these red numbers, 2 plus 2 plus 4, you get 8, which is also the atomic number and total number of electrons in oxygen. Now I need to teach you something weird. You see, as we go from left to right, from the s block to the p block elements, we eventually get to row 4, which begins with 4s electrons at element number 19, potassium. You'll notice as we move from potassium here in row 4 to calcium, element number 20, and then to scandium, which is element number 21, we now enter the D block. Please note that even though the first D block element, scandium, element number 21, is on row 4, the D block actually reverts back one number. So beginning with row 4, number 21, the first row in the D block actually starts with 3D instead of 4D when we assign electron configurations. Something similar happens in the F block. As we go across row 6 from cesium, element 55, to barium, number 56, the next element on the periodic table is actually lanthanum, number 57, the first element in the F block, which is often shown beneath the other 3 blocks on a traditional periodic table. We should note that even though the F block begins on row 6, the first F block element, lanthanum, number 57, actually has a 4F configuration. Now don't worry, I'll explain these oddities later on. So let's now get to a question that I designed specifically for this lecture. I want you to write the electron configurations of each of the following elements. nitrogen, sodium, and phosphorus. Now don't worry, I'm going to do some of these examples momentarily. If you want to, though, you can pause it right now and attempt them on your own before you see me do them for you.
Problem A asks us to write down the electron configuration for nitrogen. If we look at the periodic table, we can see that nitrogen is found in box number 7 on the periodic table. So what we do then is we start looking at the periodic table and and we count up how many s and p electrons we have in each shell. Now, I don't have a periodic table here on my piece of paper, so what I'm going to do is attempt to draw from my memory what the periodic table looks like. My apologies for not having the helium and the neon line up as they should. Nevertheless, we're trying to come up with an electron configuration for this element right here, nitrogen. You'll remember then that the first row corresponds to a 1s orbital. So we count the first row, 1s, 1, 2. So I write 1s2. Then we move on to the second row, which in this block is 2s. So I've now got 2s, 1, 2. Now, if I get over here, I'm in the p block, and p's start with 2p. I now count 1, 2, 3. That is the electron configuration for nitrogen. Let's now do the electron configuration for sodium. Once again, we have to look at our periodic table and realize that sodium is element number 11. So sodium actually appears on the periodic table right here. Sodium is the first element in the 3s block, or sorry, the 3s row within the s block. So what that means is that sodium has the electron configuration 1s2, 2s2, and in the 2p block I count 1, 2, 3, 4, 5, 6. 2p6. And then as I go back here to the 3s, sodium is the first element in the 3s row. I'll let you guys do the final question in this set, coming up with the electron configuration for phosphorus.
Now to me this feels like a wonderful place to conclude our lecture for now. But don't celebrate yet. This is not the end of our Chapter 6 lecture. You see, I divided this PowerPoint video presentation into 2 parts. So as soon as you finish this one, please watch the second part, which is my final installment on the electronic structure of atoms.